Module 3, Investigation 6, Exploring the Difference Quotient. So I should just probably say the difference quotient is just a type of average rate of change. Anyways, number 1. Recall that the volume of a box V, measured in cubic inches as a function of the length of the side of the square cutout x measured in inches, is given by the function f of x equals x times 11 minus 2x times 8.5 minus 2x. Describe the meaning of each of the following expressions in the context of the situation. F of x plus 3. So remember f, it takes lengths of the side of the square cutout as its input and its output is volume. So f of x plus 3 is the volume of a box whose length of the side of the square cutout is x plus 3 inches. Alright, f of x plus 3 minus f of x. So here we're going to have a change in the volume of the box as the length of the side of the cutout increases from its initial value of x to its final value of x plus 3 inches. So I looked at that and saw change. The book described it a little bit simpler as the expression represents the difference in volume of the box for a length of cutout of x plus 3 inches and for volume of the box for a length of cutout x inches. So there is a difference here. It may represent, well, it also represents the change as the box length increases from x to x plus 3 inches. Part 3, f of x plus 3 minus f of x over x plus 3 minus x. I hope you can see that this is a change in volume divided by a change in the length of the cutout. This is just the average rate of change of the volume of a box for an increase of 3 inches from a value of x to a value of x plus 3 inches. Remember that average rate of change is just the change in output over the change in input, the constant change that would give us the same change in output for the same change in input. Now we're going to evaluate f of x plus 3 minus f of x over x plus 3 when x equals 0.5, and then describe the meaning of this value in the context of the situation. So I've rewritten our expression for our average rate of change here. Change in volume over change in side length, change in output over change in input. But we know that x is 0.5, so we can just replace all our x's with 0.5. Okay, then we have this equation here. Now, in the numerator, let's see, we can simplify a little bit. 0.5 plus 3 is just f of 3.5. And then in our denominator, we can simplify also. Notice that in the denominator we have 0.5 plus 3. We don't really need those parentheses for any good reason. 0.5 minus 0.5 is 0. And so we're just left with 3 in our denominator. So let's just put 3 right here. So far so good. Okay, now f of 3.5, that's just the volume when the input, the side length is 3.5. So we can just use our formula. F of x is x times 11 minus 2x, 8.5 minus 2x, right over here. And so f of 3.5 is just 3.5, 11 minus 2 times 3.5 times 8.5 minus 2 times 3.5. So that's f of 3.5. And we're just going to keep on with our equality here. And I'm going to write 3.5, 11 minus 2 times 3.5. And 8.5 minus 2 times 3.5. I think I'm going to run out of room here because Now we have to subtract, so this subtraction sign here, f of 5, which is 0.5, 11 minus 2 times 0.5, times 8.5 minus 2 times 0.5. I think I just can fit that in there. And then all that is divided by 3. Okay, now we just need to simplify and get an answer. So I probably will skip a few steps here, but you can do 3.5 and then 11 minus 2 times 3.5 is, let's see, 7. So 11 minus 7. Here we also have 8.5 minus 7. Minus our 0.5. 11 minus 2 times 0.5. 2 times a half is just 1. So we have 8.5 minus 1 as well. And all of that over 3. Okay, so next we can just simplify what's in those parentheses. You could plug it into your calculator, but we'll do a couple more steps. 3 times 4 times 1.5 minus 0.5 times 10 times 7.5 all over 3. Forgot a 0.5 here. So I'm just going to plug this in my calculator. Get negative 16.5 for the numerator. So negative 16.5 divided by 3 is negative 5.5. So there we have our average rate of change. We need to describe the meaning of this value in the context. So what we have is the average rate of change as our cutout length increased from 0.5 to 3.5. So the average rate of change of the volume with respect to the length of the square length. So the average rate of change of the volume of a box for an increase of the length of the side of the cutout from 0.5 inches to 3.5 inches is negative 5.5 cubic inches per inch of length of the side of the cutout. So make sure we know where these numbers are coming from. There's the negative 5.5, which is a change in volume over a change in length. So that's the units are cubic inches per inch. And then we increased from 0.5 to 3.5 inches. Notice that up here we just have the final volume of the box, which would be 3.5 inches. Pretty good to see it here. The volume at 3.5 inches minus the volume at ½ an inch divided by that change in the length of the side of the cutout, 3. Because our initial value was 0.5, our final value was 0.5 plus 3, or 3.5. So let's take this idea of average rate of change and look at the graph of the function. Remember that we had the volume of the box, f of x equals x minus, or x times 11 minus 2x, 8.5 minus 2x, and then we had this graph that we looked at in class. So let's think about what this means. Remember, x was 0.5, or 1/2. So that's right here in our box, and again the x-axis, the input, is the length of the corner cut in inches, and the y-axis is the volume of the box in cubic inches. And so we said that that average rate of change, let's just go look back at this again. X is 0.5, that's why I put 0.5 on the graph, and then we have the change in x, we add 3 to x. So it's really the change is from 0.5 to 3.5. So 3.5 is about right here, and Notice that 0.5, if that's the input, the output looks to be, it's hard for me to judge this, maybe somewhere about right here. And if 3.5 is the input, the output looks to be about right here. And we had a change of a positive 3. And we can represent that on the graph like so. This line here is our change in x, which is 3. And then notice that we have a change in volume, a decrease. So let's see, change in x from that way, increase, and then our change in volume is a decrease. Now remember that change in volume, that was f of x plus 3 minus f of x, or f of 3.5 minus f of 0.5. And we found out that our average rate of change, our change in f over the change in x, was negative 5.5. And what does that mean on this graph? Well, if we take this point here, negative 0.5 in this output, and this point here, 3.5 in this output, the average rate of change is the slope of the line that connects those 2 points. Notice that there's a negative slope of this line, and we should go down 5.5 for every one change in x. You should also be able to connect this to the slope. We just have a change in y over a change in x, a change in output over a change in x. That's all this average rate of change formula is. It's a change in y over a change in x, change in output over change in input, or slope. Question number 2 says the area measured in square feet of a circular oil leak as a function of the amount of time measured in minutes since the oil leak started is given by the function g of t equals 7.84 pi t squared. Describe the meaning of g of t plus 5 minus g of t over 5, which is just a simplified form of g of t plus 5 minus g of t over t plus 5 minus t in the context of the situation. I hope you noticed that we simply have a change in area of the circular oil leak, g of t plus 5 minus g of t, divided by a change in time, just 5, or we increase from the time t to the time t plus 5. And so this just represents the average rate of change. The average rate of change, more specifically, of the area of the oil slick for an increase of time of 5 minutes. The change in the area of the oil slick if the change in time is 5 minutes. Next, for part B, we're going to evaluate g of t plus 5 minus g of t over 5, just that average rate of change when t is 1.5, and then describe the meaning of this value. So notice all we really need is to find g of t plus 5, subtract g of t, and divide by 5. Let's do this step by step. One step of the problem is simply to calculate g of t plus 5 when t is 1.5. g of t plus 5 equals g of 1.5 plus 5, which is g of 6.5. That just means we need to evaluate the function g when t is 6.5, so we just substitute 6.5 in for t. That gives us 7.84 pi times 6.5 squared, or 1040.62. Now let's look at g of t. We're calculating g of t because it's this next piece of the formula. G of t is, since t is 1.5, it's g of 1.5, which, looking at our formula here, is just 7.84 pi times 1.5 squared. Using our calculators, 55.42. So now we can go back to our main function. G of t plus 5, we know what that number is, minus g of t, we know what that number is, divided by 5. So 1040.62 minus 55.42 over 5. We got that because we needed g of t plus 5 minus g of t over 5. and the average rate of change turns out to be 197.04. Now let's describe the meaning of this value. So remember, this was a change in G over change in time. This is the average rate of change of the area of the oil slick as the time increases from 1.5 minutes to 6.5 minutes. And that's 197.04 feet squared per minute. Notice the units: feet squared, area, per minute, time. So in general, the expression f of x plus h minus f of x over h, which is a simplified form of f of x plus h minus f of x over x plus h minus x, where h represents the change in x, is called the difference quotient. So that's the change in input is h, and this is the change in output, f of x plus h minus f of x. The difference quotient is the average rate of change for a function between two input-output pairs, say point A to point B as expressed in the graph below. Using function notation, we say that you can find the average rate of change between any 2 points, x f of x and x plus h f of x plus h, by computing the change in outputs over the change in inputs, f of x plus h minus f of x over x plus h minus x, or simply f of x plus h minus f of x over h. You should recognize this as the simple slope formula, y2 minus y1 over x2 minus x1. Thus, when finding the difference quotient for 2 points on a function, you are determining the average rate of change between those two input-output pairs. So here we have our graph. There's x, then we have x plus h over here, so there's a change in x, or a change in input of length h. Then we have our change in the output. This point is f of x plus h, that's the y value, and this point, the output, is f of x. So our change is f of x plus h minus x, as we saw on this graph over here. The f of x plus h minus f of x, that's the change in the output. And again, the average rate of change is the slope of the line that connects those 2 points. Number 3, find and interpret the difference quotient, average rate of change, for the population of a small town, P, measured in number of people, as a function of the number of years t since 1990 as defined by the function f of t equals 1500 plus 60t. We want to find the difference quotient, and the difference quotient just has an arbitrary change in x of h. So we just need f of x plus h minus f of x over h. Well, here our input is t, so we need f of t plus h minus f of t over h. Then f of t plus h, well, here's f of t. F of t plus h is simply 1500 plus 60. And in place of t, we're having t plus h. So that's f of t plus h. I'm just going to put that in brackets. Then we're subtracting f of t, which is just 1500 plus 60t. And we divide by h. So let's simplify this. So 1500, that 60 will distribute. We'll have 60t plus 60h minus the negative will distribute also here, 1500 minus 60t, and all that's over h. Then notice that the 60t here and the negative 60t here will cancel out. Also the 1500 and the negative 1500 will cancel out. That gives us 60h over h, or just 60. That's the difference quotient, the average rate of change, which, remember, is the slope which we have a linear function here, 1500 plus 60t. That's in the form y equals b plus mx, just mx plus b reversed. We see our slope is 60, our average rate of change is 60. No matter what difference in t we pick, no matter what change in t, h we pick, the average rate of change will always be 60, because the average rate of change is the constant rate of change needed to have the same change in output for each change in input. And when you have a straight line, then no matter which 2 points you pick, the average rate of change, the change in this case t, or the change in f with respect to the change in t, is always the same, because it's a constant rate of change the whole way up and down this line. Part B. Find and interpret the difference quotient for the distance a car is from an intersection D, measured in feet as a function of time t, as defined by the function m of t equals 2t squared plus 4t plus 1. First, we write our difference quotient formula using m and t. That's m of t plus h minus m of t over h. Next, we'll evaluate m of t plus h, just plugging in t plus h for all these t's, and we'll subtract m of t, which is just this expression right here. Notice I put parentheses around the m of t because this is just one number. We have to put parentheses around it or we won't be subtracting the whole number, only part of it. Now we're going to simplify this mess. The big deal here that you have to remember, some of your algebra, is that t plus h squared is t plus h times t plus h. Now you can distribute that 4, that's 4t plus 4h plus 1, and distribute your negative here. So we get this, and everything's over h. Now we keep simplifying. Here we have to multiply t plus h times t plus h. T times t, t squared, t times h is th. Really we'll have another t times h, that's 2th plus h squared. Let me know if you have trouble with that calculation. We can go over it. Then over here, lots of stuff simplifies. 4t, negative 4t cancels out, positive 1, negative 1 cancels out, so we have positive 4h minus 2t squared left over, and then all that's over h. Now we can distribute this 2. So we have 2t squared plus 4th plus 2h squared plus 4h minus 2t squared all over h. Now again, notice what cancels, 2t squared and negative 2t squared. So we're left with the following, 4th plus 2h squared over h, this piece in the middle. Now notice each piece has an h, each term has an h. We can factor out an h as follows. Now h divided by h is 1, so we can cancel these h's, and we're left with 4t plus 2h plus 4, which is our difference quotient. So, no matter what the difference in time is, h, the change in output, m, over the change in time is always 4t plus 2h plus 4. Number 4. Use the graph of y equals f of x below and an input value of x equals k to denote the following quantities on the graph. So k is just a random input value. It's arbitrary. It could represent any number. And we want to, for part A, represent f of k on the graph. So notice that this is the curve, y equals f of x. It's the function, the set of all outputs, or inputs and outputs. So when k is the input, you can see that the output is right here. That is f of k. So again, f of k is this y value. And this point right here, this point, the input is k, and the output is f of k. Alright, so that's a little bit too much, but f of k for part A is just this y value. Now k plus 2.5, well, we just take k and we add 2.5. So maybe somewhere about right here. This distance here would be 2.5. So we just add 2.5 to k. Let's see, and note that that brings up a new point. So here in part C we have f of k plus 2.5. Think about that. If our input is k plus 2.5, then here's the output right on the y-axis over here, f of k plus 2.5. I'm not sure what your part C is. It could just be f of k plus 2.5, which we've represented right here. That makes more sense than what I see for part C right here. So let's skip part C just for a second. Let's look at part D. F of k plus 2.5 minus f of k. So that's a change in output. F of k plus 2.5 minus f of k. We could look at it, it's just this distance here. We could also look at the same distance. Over here it's the change from, let's say we go to this change in 2.5 here, then the change in y up here, that's the f of k plus 2.5 minus f of k. And here this is our change, and x is 2.5. Now I think we're ready for part C. F of k plus 2.5 minus f of k over 2.5, that's just going to be the slope of the line connecting this point here, h of f of k, and this point here, which is k plus 2.5 f of k plus 2.5. So once again, this point right here is k plus 2.5 f of k plus 2.5, and then if we make the line connecting this point, h f of k, and the second one, k 2.5 f of 2.5, the slope of that line is this value here, f of k plus 2.5 minus f of k over 2.5. And again, see, it's just a change in f over a change in x, a change in y over a change in x, or the slope between these 2 points. Notice it's y2 minus y1 over x2 minus x1, and those k's would cancel out and give us 2.5 when we subtracted that. So all of these are really big ideas in calculus. In fact, the difference quotient is half of the derivative. The derivative is really the limit as this h goes to 0 with the difference quotient.